Now, we're going to have a look at the equations of motion in an angular or rotational motion frame or in a linear frame. And we'll see that they actually correspond extremely well. Remember, just like for kinematics, this is for a case of 0 alpha, that is angular acceleration, and 0 a, that is linear acceleration. If we have multiple cases within a problem, we have to split them up. So this is the one for angular velocity. Angular velocity is the initial angular velocity plus the acceleration, angular acceleration times the time. That corresponds very nicely to this one. Has exactly the same form. Angular displacement. I've not put theta naught in here because I'm assuming it's 0. So I'll do the same thing on the other side. So you won't see x equals x naught plus b naught 2 plus half 8d squared. What you see is just this, right? I've said x naught is 0 here. You can put it in if you need to. But fundamentally you can see that they're exactly the same form. And now we look at the form for where we've put a couple of these together to get rid of the time constant. And what we end up with is omega squared equals omega naught squared plus 2 times the angular frequency alpha times delta theta, the change in angle. In this particular case, we've got v squared equals v naught squared plus 2a delta x. So what we've got is a very nice correspondence between the two. All right, so the average angular velocity, you just sum the final angular velocity and the initial angular velocity divided by 2. The same is true of the average linear velocity. So although this might seem initially to be very, very complicated, really what it comes down to is just understanding the meaning of omega, right? The meaning of alpha, the meaning of theta, and relating it to these ones here, which you're already very familiar with, right? So that's why I've given you quite a few problems to practice looking at theta, omega, and alpha. Okay, here's an example. A centrifuge rotor is accelerated from rest to 20,000 RPM in 5 minutes. What is its average angular acceleration? What is an RPM? Rotations or revolutions per minute, right. So that's really not a standard unit for us, right? We want always to be in rotations or revolutions per second, which is going to give us hertz. We're being asked to find the average angular acceleration, which is the change in angular velocity divided by the change in time. That's exactly equivalent to the average linear acceleration, right? The initial angular velocity is 0, and the final angular velocity is given by this. Omega equals 2 pi, where this f is the final frequency. So that's 2 pi radians per revolution, right? That's what this is telling us. There's 2 pi radians per revolution times 20,000 revolutions per minute divided by 60 seconds per minute, and we end up with the correct units. It's actually about 2,090 radians per second if you do it exactly. Then, because delta t is 5 minutes or 300 seconds, we want to find the average. So it's going to be the final angular velocity minus the initial divided by the time, which is 2100 radians per second minus 0 because it was at rest, divided by 300 seconds, or 7 radians per second squared. Okay? Through how many revolutions has the centrifuge rotor turned during its acceleration period, assuming constant angular acceleration? Well, we decode, we've got omega naught is 0, omega is 2100 radians per second, alpha is 7 radians per second squared, t is 300 seconds. So we need to find the total angular displacement. Total angular displacement is going to be given by this. Right? This looks very much like linear kinematics, doesn't it? And we put the numbers in, and we get out of that 3.15 by 10 to the 5th radians. We now need to convert the angular displacement to revolutions, but by dividing by 2 pi. So, if we've got 3.15 by 10 to the 5th radians divided by 2 pi radians per revolution, right? 2 pi radians is a circle. So there are 2 pi radians in one revolution. And we were asked to find how many revolutions. We get 5 by 10 to the 4th revolution.